One of Stephen's favorite subjects is eternal inflation. And so therefore I thought I'd give Stephen as a birthday present a new version of our paper on eternal inflation. Now this paper itself is also eternal in the sense that I am not sure whether we will complete it in a finite time. But I'm happy to talk about it, which I will do. Now, it might be surprising why is Stephen interested in eternal inflation? Because after all, the no-boundary wave function is a ground state wave function, and it predicts only a few e-folds of inflation. But Stephen's interest in eternal inflation goes back to 2006, 2007, when he realized that the no-boundary probabilities for entire universes are weighted by the volume of surfaces of constant density when you transform those probabilities into probabilities for our local observations. And the reason is that you have to take into account the possible locations of our past light cone, to move it around a constant density surface. And of course, that favors large universes, the ones with a regime of eternal inflation. Now, the reason that even Slava should be interested in eternal inflation is that it matters for our observations. And this is extremely simple to illustrate. Take this model of inflation. You could roll down from the right or from the left. And imagine both sides are distinct by a different tensor to scalar ratio in the perturbations. And imagine Aichiro calls up Slava and he asks him, well, I'm going to launch a new satellite. What does your theory predict? Am I going to observe tensors rolling down from the blue side, or am I not going to observe tensors rolling down from the red side? At that point, Slava will need a theory of eternal inflation in order to answer Aichiro's question. So, how does eternal inflation manifest itself in the no-boundary wave function? Well, let's start with slow roll inflation. Slow roll inflation from a wave function perspective is described as, well, the wave function oscillates rapidly and it predicts an approximately classical slow roll down the hill. And this is because in slow roll inflation, the wave function of the fluctuations, zeta, is a narrow Gaussian. The variance is small, h squared over epsilon. And therefore, the wave function is pretty much peaked around the approximately homogeneous isotropic background, which inflates and leads to small ripples at late time, which we observe in the CMB. Now, eternal inflation is different. Eternal inflation happens higher up the potential, where the potential has a flatter patch before you enter the slow roll era at later times. Now, if you look at the wave function of the fluctuations high up the potential in the regime of eternal inflation, you find that the wave function is no longer narrowly peaked. The variance of the wave function of the fluctuations in eternal inflation is large. Therefore, even if you might want to start with a classical slow roll, the dynamics in the regime of eternal inflation is not at all that of a classical space-time. In fact, the dynamics of eternal inflation is governed by the quantum dynamics of the fluctuations and their back reaction on the geometry. Toy models to take into account this quantum dynamics have led to the picture of wildly irregular reheating or constant density surfaces on the scales associated with eternal inflation. In fact, toy models suggest that constant density surfaces become infinitely large in eternal inflation. So in a way, eternal inflation is an instability of slow roll inflation in which the fluctuations are no longer suppressed and Gaussian on those large scales, but unsuppressed, and much of the probability moves towards wildly irregular configurations or spacetimes. So we want to say that basically this is telling us that the usual theory of inflation based on semi-classical gravity breaks down in eternal inflation. And in this paper, we want to put forward a different theory, which is not based on semi-classical gravity, and we would use holography to do so. So really, we want to replace the good old no-boundary wave function by something else. But of course, an entire wave function of the universe, replacing it, that's a lot to replace. Because the wave function describes, it's a function of the configuration on some space-like surface. So it describes an entire ensemble of spacetimes. And we want to use holography to define, so to speak, to specify a wave function directly on a surface sigma of constant density. So how are we going about doing this? Well, holography, gauge gravity duality in general, has been developed over the last few years in the de Sitter context. Wait, this is really delicate. And so let me briefly review that so that I can then apply it to our problem of eternal inflation. So this is the good old representation of the no-boundary saddle points. They consist, you should think of these as complexified solutions of Einstein gravity coupled to a scalar field and so forth, which really consist of a Euclidean regime where the solution is an approximate force sphere that gradually transitions into a Lorentzian inflationary asymptotic de Sitter space if your theory has a cosmological constant. The boundary conditions are that your solution tends to the final configuration, which is the argument of your wave function, h for the metric and chi for the scalar field, and that the solution is everywhere regular. So there's a regularity condition at the origin. As I said, you should think of these solutions as complexified solutions of the Einstein equations, which means that the action, which is what counts, what specifies the wave function, the action includes an integral over complex time. And the usual representation, which I just show, of those saddle points is really a representation in which we follow those solutions along a particular contour, going horizontally first and vertically upward. That's a contour which first has a Euclidean region and then gradually becomes Lorentzian de Sitter space. But nothing prevents us to go from the origin, the south pole, to the end point where we evaluate the wave function along a different contour. These are complex analytic solutions. You can shift the contour around, and the only thing which matters is the action of this saddle point, which determines the wave function. So a couple of years ago, it became clear that the no-boundary saddle points have a different geometric representation in which the Euclidean interior region is basically a Euclidean anti-de Sitter domain wall region. So at the saddle point level, at the wave function level, without bothering about any sort of analytic continuation, there is pretty much an automatic connection between Euclidean ADS and Lorentzian de Sitter. Now, this connection becomes interesting when you evaluate the wave function, when you decide on a good day to evaluate the wave function along this different contour. Then you find that the contribution from the first part of the ADS contour, so this one, is basically what we call in ADS-CFT the regularized ADS action plus the divergent surface terms. The contribution from the second part of the contour automatically regularizes those, provides minus the surface terms and adds a lot of phase to the wave function. The phase is physical and important because the phase is what makes the wave function oscillate and predict classical evolution in the large 3-volume regime. But you notice that the weighting of the different saddle points in this new representation is given entirely by the Euclidean ADS domain wall region of the saddle points. That is interesting because we know something about holography in Euclidean ADS, we can replace it with a dual field theory on the asymptotic ATS region, so to speak. So this was our proposal for the holographic form of the semi-classical no-boundary wave function. Evidently, this is a construction which holds at a saddle point level. And for those of you who are now worried that it's minus it's 1 over the partition function that enters, by the partition function here, I mean the Euclidean ADS CFT dual and not a new DS CFT dual or so. So this is in line, for instance, if you remember the story with the higher spin gravity duality, the partition function of the SPN models is 1 over the partition function of the ON models. So it's not so different. So I want to apply this prescription now to excise just the regime of eternal inflation. So let's go back to this toy model that I showed earlier. There are clearly 2 different regimes here. If my scalar field is everywhere small, then below a critical value, which we identify as the onset of eternal inflation, then it's slow roll inflation all the way down to where the saddle point rounds off the evolution. In that case, there's no eternal inflation. These are perfectly valid no-boundary saddle points. One is always in the same classical gravity regime. And that regime translates in having a small deformation. So there's a link between the scalar field in the wave function and a source for a scalar deformation in the partition function. If the scalar field is everywhere small, the source is small as well. So what is the regime of eternal inflation from this perspective? It's the second regime corresponding to a large deformation, which somehow takes the dual field theory towards a completely different IR. The time evolution of the inflationary universe corresponds in the dual field theory to an RG flow from the UV back to the IR in the past. And somehow there's a phase transition at a critical value of the deformation where the RG flow takes you to a very different IR, where semi-classical gravity does not hold, and so forth. Whereas in slow roll inflation, what is the holographic dual description or prescription of the no-boundary wave function? I would say it's probably a trivial IR fixed point corresponding to the geometry capping off. So we want to replace the regime of eternal inflation. So we want to evaluate the wave function back in the past, deep into the regime of eternal inflation, where the scalar field takes that critical value high up the potential. And there we want to use our prescription for DSCFT and replace this with a dual partition function. Because we're deep in the regime of eternal inflation, in fact, we're close to the IR of the field theory. And so the dual here will be an IR CFT obtained from that flow, deformed by a certain deformation, alpha tilde here, which becomes important at the exit or at the threshold for eternal inflation. So this is schematically the picture of what we're doing. As I just said, so the dual is an IR CFT defined on an inner boundary at the threshold of eternal inflation and deformed by a low dimension irrelevant operator that becomes important at the threshold. Why low dimension? Because eternal inflation is really an approximate ADS or de Sitter regime of those inner saddle points. So now I think there are 2 things to do. One is, of course, are there any observational implications of this prescription? And the first observational explorations of perturbations and so forth are being explored by McFadden and Skenderis and others in related models. But I want to focus here on the implications of this proposal for the global structure of the universe. So the idea here is that that partition function replaces the wave function of the universe on that exit surface of eternal inflation. So it's now going to be the partition function that specifies the amplitude of different shapes for the exit surface of eternal inflation on that inner boundary. And you immediately see that holography provides a very different perspective on the kind of exit surface, the kind of infinities that I referred to earlier, which emerge from a semi-classical gravity analysis of eternal inflation. For instance, just locally around the round sphere, no eternal inflation, just does the homogeneous isotropic universe remain a maximum of the probability distribution? Well, that is fairly generally true. In fact, the F theorem and related recent results of certain spin-2 deformations of field theories all point towards the conclusion that locally at least the homogeneous isotropic histories have maximum probability. So already that is naturally rather different than the story you hear in eternal inflation. Moving on to global features of the probability distribution, they're of course extremely hard to calculate because you would have to evaluate partition functions for a wide range of different deformations and geometries. But there are a few things we can say. And one characteristic feature of these widely irregular surfaces in eternal inflation is that they have patches where locally the curvature is negative. Those are bubble-like patches, if you wish, in this very fractal-like grand surface of constant density. But those immediately appear very dangerous from a holographic point of view, because if the curvature is negative, because the curvature couples to the scalars of the field theory, they have an effective mass. They become tachyonic scalars. That means it's likely that the partition function of those field theories on such deformed geometries is likely going to diverge. But if the partition function diverges, then the probability of such wildly irregular surfaces is going to vanish. Of course, that's a qualitative argument. You could imagine strongly interacting field theories which somehow stabilize themselves even on geometries with negative Ricci scalar. And then it really is going to depend on I think, the intricate details of the theory, how this will play out. But we pursued one sort of toy model context to gain a little more quantitative insight in this, and that is the following. We evaluated the partition function in a kind of extended mini-superspace model, which includes boundary geometries with a negative curvature, as well as deformations, mass deformations, alpha, that are dual to bulk scalars driving eternal inflation. The extended mini-superspace model consists of these double squashed spheres, which are future boundary configurations of anisotropic inflationary universes, really. And in the space of squashed spheres, you clearly have regions, the blue regions here, where the Ricci scalar is negative. Now, of course, we can't evaluate the partition function for the ABGM theory, dual to Einstein gravity, and so forth. We have to resort to a simpler model consisting of a collection of scalars known as the three-dimensional critical ON vector model. Why do I choose the critical model? Well, first of all, because it's interacting, and second of all, because this is the one which is dual to the wave function in the usual field space. So evaluating the partition function of such a toy model field theory for a range of mass deformations corresponding to inflationary universes on a squashed sphere corresponding to anisotropies inducing negative curvature is a long numerical exercise, basically, which I won't go into, but it did reveal that there is absolutely no spreading of that probability distribution into these negative curvature domains of superspace. The probability distribution remains nicely localized around the more homogeneous isotropic configurations. So these three little pieces of evidence, the connection with the F-theorems in field theory, the general qualitative argument that negative curvature patches are going to make the partition function diverge, and this toy model lead us to conjecture that, in fact, the exit from eternal inflation is smoother and globally finite than what semi-classical gravity has indicated for all these years. So pictorially, we would say that in a way you could think about this, that the dual field theory prescription somehow regularizes the dynamics of eternal inflation. As Jim mentioned, this is not unlike what we pursued or what we argued a long time ago, that for the purpose of local observations in eternal inflation, we could as well coarse grain over all these massively large-scale big fluctuations. But at that time, we didn't have an argument that back reaction would be negligible. So you can't really conclude that there's no effect from the large scales onto the small scales, and therefore you're sort of limited in deriving any subtle predictions from that bigger structure. So hopefully this new scheme will help us with that. So it won't have escaped your notice that this is a rather different view of the no-boundary proposal, and I think it testifies to Stephen's many qualities, that he, at 75, can still change persuasion. There is a past boundary now. It's no boundary with a boundary. Beyond which, we want to argue that semi-classical gravity interpretation in terms of space-time does not hold. So in a way, it is eternal, in the sense that the regime of eternal inflation is timeless. Now, there's no notion of time beyond that surface. Evidently, the transition, I mean, I've talked about a sharp transition from eternal inflation hubs to slow roll. Evidently, more refined models or more development of this scheme will detail how that transition happens, in particular, how the field theory degrees of freedom on this inner boundary couple to the bulk dynamics and potentially lead to observational signatures. So that was my the main point I wanted to make. But because multiverses seem to be a common theme today, I thought I would conclude with a few words on the multiverse. You might wonder, well, suppose for a moment this is all true. What are the implications for the multiverse paradigm? Well, imagine for a moment this generalizes to false vacuum models of eternal inflation. I've been talking just about slow roll eternal inflation. But imagine this smoothing of the large-scale structure of our universe generalizes to those models. It seemed to me that this would imply a significant reduction of the multiverse, which really should not come as a surprise, because after all, holography specifies a fairly rigid, asymptotic de Sitter structure. How are you going to put in an extremely complicated fractal-like universe if your asymptotic structure is given? That doesn't sound compatible. So I think, and I see this as a positive thing, holography, in my view, might give us a handle on that complicated multiverse by reducing it and make it fit into a more rigid structure. Now, are we down to one universe? Well, I don't think so, because there are still, just think about field theories, there are still many irrelevant deformations that you can imagine to exit from eternal inflation, or vice versa. If you think from a UV perspective, there are all sorts of flows that you can imagine which contribute, which you can harbor in a given asymptotic structure. So Martin showed us yesterday this slide. How many Big Bangs there are, he asked. One or many? And it came down to choice. Is there any role of entropic reasoning in cosmology? And we've heard a few opinions this morning. So where do we stand on that? Well, for once, Stephen seems to be politically correct. We stand somewhere in the middle, I think, where there is a reduction of the multiverse, but clearly not just one universe. There are still plenty of directions, given an asymptotic structure, different field directions in field space, which potentially could lead to different kinds of inflationary histories. So, all the rest you'll see in our paper one day. Happy birthday, Stephen.
Thank you very much. Some questions? Yes, Gary?
Hi, is there anything special about the threshold of eternal inflation? Could you imagine moving the boundary to different scales, and would it be invariant under that?
We were motivated to put the field theory at the threshold because that's the clearest indication we have where semi-classical gravity breaks down. But you could imagine a variety of models where that boundary is indeed moved. And for instance, Skenderis has basically, as far as the fluctuation story is concerned, put the boundary all the way at the end of inflation, right? That gives you...
Yep.
Just a general question to you and probably to Jamer also. The word string theory hasn't been mentioned that much in these talks, but you're assuming there is an ultraviolet completion of whatever our theory is. And so you're using a bit ADS-CFT, but do you think it's enough to deal in that level, or do you eventually will need a full string theory to deal with all those questions?
Well, I think of ADS-CFT as full string theory. What you're really asking is, the models we know now in ADS-CFT, I suppose that's the answer. Can they, how are they going to act in this de Sitter domain of the wave function? So they enter as dual theories, as 1 over the partition function of an ADS-CFT dual theory. But it's a very subtle question as to what deformations you allow in order for your wave function, defined this way, to be normalizable, to be physically meaningful, and so forth. I think there's a lot of work that has to go into that question. Yeah, secondly, my derivation, so to speak, of the holographic form of the no-boundary wave function was all done at the semi-classical level. You might want to look into 1 over n corrections and so forth, which we haven't touched at all. But which, in this spirit, would be also defined or specified by the dual theory.
Thanks.
Okay, so if there are no more questions, let's thank Thomas again and we'll break for coffee.